Okay. So page 4 of 4.1 notes. Okay, so this is page 4 of 4.1. So we just got done talking about the linear correlation coefficient R. Now example 3 says, compute the linear correlation coefficient R for the data in example 1. Is there a strong linear correlation between the variables? Is it a positive or negative correlation? So to do this, we're going to go to StatCrunch, right? So like we said, we're not going to do this by hand. It would just take us way too long. So go ahead and open up StatCrunch so you can follow along with what I'm doing. Okay. It says to compute the linear correlation coefficient for the data in example 1. So I'm going to flip back to the first page so that I can see that data. And it's right there in that table on the first page where it says number of absences and final grade. And in fact, I'm going to call this number of absences and final grade. And when you enter this data, these are ordered pairs, right? So they have to match up. So you have to make sure that you get them, 6 has to correspond to 82, you know what I mean? So they have to be entered that way. So make sure you get them in the right order. So I'm gonna go ahead and enter this in. Okay, let me just make sure I got it all in there correctly. See, and you guys aren't here to check my work, so that makes me a little nervous. But I think I've got it all in there correctly. Okay, so we weren't asked to do this in this particular example that we're looking at right now, but let's say that we wanted to make a scatter plot of this, okay? So you go to graph and then scatter plot, right? And then you have to tell StatCrunch which one represents your X variable and which one represents your Y variable. In this case, we wanted the number of absences to be X and we wanted the final grade to be Y. And then that's all you need to do. You just hit compute and it makes a nice little scatter plot, which is fairly similar looking to the one that we drew by hand, I think. I would say definitely a negative linear correlation here. But to be certain of that, now we could compute the correlation coefficient R. So to do that, we go to Stat, Summary Stats, and Correlation. Okay? Stat, Summary Stats, Correlation. You have to select the columns that you want to determine if there's a linear correlation between. If you just click one time on each of these, it's just going to switch back and forth between them. So you have to hold down and drag so that it'll select both of them. The other option would be to hold down Control and then click on both of them, right? And then that's all you need to do. You don't need to click anything else. You just click on those variables, hit compute, and there it gives us the correlation coefficient of negative 0.944. Remember, the closer the R is to -1, the stronger the negative correlation. The closer R is to +1, the stronger the positive correlation. In this case, we're really close to -1, right? Negative 0.944. So I would say there's a strong negative linear correlation between these two variables. Okay. So going back to the notes, let's write that stuff down. Okay. So we just did this in StatCrunch, right? The linear correlation coefficient R was approximately 0.944. We usually round these to 3 decimal places. Okay. Sorry, it was negative. So R is approximately negative 0.944. Okay. So is there a strong linear correlation between the variables? Yes, and it's negative, right? So we'd say there is a strong negative linear correlation. Okay. Now, even still, you might have some close calls, right? You might. So here we got negative 0.944. Pretty clearly, that's pretty clearly an indication that there's a strong correlation. But what if you got like negative 0.6, right? Is that good enough to say that there's a linear correlation or not? So to answer that question, we use a table of critical values. And in fact, in this table, I'm going to relabel this CV for critical value. So depending on your sample size, you're going to have a particular critical value, and this is the number that you have to beat, right? So your correlation coefficient needs to be bigger than the critical value in order for you to determine that there's a linear correlation. So let's say that you had 22 data points, right, in your data set. Then in order for you to determine that there's a linear correlation, your correlation coefficient R needs to be at least 0.423, right? So at least 0.423 if your sample size is 22, right? As you can see, the numbers go down, right? The larger your sample size, the smaller the critical value, right? The smaller the linear correlation needs to be in order for you to determine that there's a linear correlation. Another way to say that is that the smaller the sample size, the larger the correlation coefficient needs to be in order to determine that there's a linear correlation. And that makes sense, right? Because the fewer the data points, the more likely there's a linear relationship between the variables, right? I mean, think about it like this. If there are only 2 data points, if your sample size is 2, then there has to be a straight line that connects those 2 points, right? So of course there's a linear correlation if you only have 2 data points. If you have 3 data points, then again, there's pretty likely to be a linear correlation there. If you have 50, it's a lot less likely, right? So consequently, our critical values have to be better and better and better the smaller and smaller our sample size is. The larger the sample size, the smaller we can get away with our correlation coefficient being and still determine that there's a linear relationship. Okay. So let me give you an example of how to use this chart. Okay. So suppose that we have 12 data points and that we go on StatCrunch and we compute the linear correlation coefficient between those 12 points, and we see that the linear correlation is negative 0.521. Okay. What we're going to do is we take the absolute value of that number, which means if it's positive, it stays positive. If it's negative, it becomes positive. So absolute value of R in this case would be positive 0.521. For 12 data points, the critical value, is 0.576, right? So 0.576 there. So the critical value is 0.576. Now the question is, can we conclude that there's a linear relationship between the variables? Well, in order to conclude that there's a linear correlation, our correlation coefficient needs to be bigger than our critical value. And as you can see, in this case, it is not, right? It's not bigger, it's smaller. And so the answer to this particular question would be no, right? So we would say something like this. We would say since absolute value of R is less than our critical value, and if it helps, you can replace those with the numbers, right? The absolute value of R, 0.521, is less than the critical value, 0.576, right? So since the absolute value of R is less than the critical value, there is not a linear correlation. Whoops, let me zoom back out. Okay. So that's how that works. I'll give you another example of that kind of from beginning to end, making a scatter plot and all that stuff. I think I'm going to start a new video though. I'm just nervous about these things getting too long because then it takes hours and hours to upload to YouTube.